Okay, in our next section, we're going to start to talk about IP routing at layer 3, where we saw before with the layer 2 Ethernet switching that the switches in the layer 2 network, they're going to be making their decision based on the hardware address or the MAC address of the hosts that goes into the MAC address table or the CAM table that eventually tells the switches what particular ports I want to send the traffic out when it's going out for just Ethernet at layer 2. Now, IP routing is going to use the same type of logic where devices in the IP network are going to use each other's destination addresses in order to figure out how the traffic is going to route, or essentially how the data is going to be sent between the different devices. So the key here is that the decision is made how the forwarding happens based on this destination address that's going to go inside of the packet. So it's the same type of logic of how the layer 2 switches are using the MAC addresses, but now it means that we're going to be doing it just based on a higher layer of the OSI model. We're doing it based on the IP packet. Now we'll see that the implication of this is that the IP routers in the network, they're then going to need to know about what are the different destinations in the network in order to send the packets. And this is what our routing protocols are going to be used to solve. So we'll talk about some different variations of these later, like RIP version 2 or EDGE-RP or OSPF, where the ultimate goal of this is that the routers need to know where are all the destinations. So when we do this routing lookup, or essentially look at the destination address in the IP packet, we're going to figure out where the packet needs to go. But before we get into the specifics of how the routers are going to do this with the different protocols, we need to know how does the end host also fit into this. So technically, the end host itself is also going to run IP routing. So whether this is like our Windows machine or a printer that's attached to the network or an IP phone, these devices technically also run IP routing as well, but their decision is going to be a little bit simpler, where they're basically going to have one of two options when they're sending traffic into the network. They need to figure out, is the destination address on my subnet? And if it is, I'm going to just go ahead and send the packet directly to them. But if the destination is in a different subnet, then I'm going to need to send it to some gateway or router on the segment that's going to route the traffic on my behalf. So technically, you can configure like Windows or Linux or Mac OS to run routing protocols like RIP or OSPF. Most of the time, you don't do this, where the simpler design is that there's going to be some router or essentially default gateway on the network that's going to be in charge of routing the packets for any destination that is outside of that local subnet or outside of that local network. So to figure this out, first thing that the end host needs to know is the destination on my subnet or is the destination on somebody else's subnet? And the way they do this is with the combination of the IP address and the subnet mask. So the address itself, we talked about, is going to be that 32-bit value, or the 4 bytes that are separated by the decimals, the dotted decimal format. But the subnet mask, which again looked at the format, like if we were to have an address that's 192.168.0.1, our subnet mask might be something like 255.255.255.0. Or in other words, our network is 192.168.0.0/24. So this is just the decimal notation of this address, or the bitwise notation, I should say. Now, the way that the hosts do this is with a binary process that is known as the AND logic gate. And what the AND logic gate says is that I'm going to take my address and I'm going to compare it to my subnet mask. Then I'm going to take their address and compare it to my subnet mask as well. Based on the result of that, I'm going to be able to figure out, are they on my network or are they on somebody else's network? And this is what's considered masking the address. So you take my local address and you run a binary AND against the subnet mask. You take the destination's address, you run that same process. If the results are equal to each other, it means that we're on the same subnet and that we don't necessarily need to send the traffic to a router in order to get it to the destination. So it could be someone who's on my local Ethernet LAN. Now, the actual operation itself the binary and, we have what's known as the truth table, or essentially the mathematical result of the calculation, where there's 4 different variations for truth tables. We're looking at 4 different possible inputs, where the case could be that my address in that individual bit place is a 0, and their address is a 0. The result is 0. If mine is a 0 and theirs is a 1, the result is 0. If mine is a 1, theirs is a 0, the result is 1. The only case where this is true, where in binary true is going to be a 1 and false is going to be a 0, it's only when both of the inputs are 1 at the same time. So the result is true if both of the inputs are true. So if we were to look at an example of this, let's say that we have 2 addresses that are 192.168.0.1 and 192.168.0.2. So this first device is trying to reach the second one. This is what we have configured in the current network from before. If we were to look at router 1 and look at the show IP interface brief, router 1 has this address assigned, 192.168.0.1. And on the link, we also have the subnet mask of /24, or 255.255.255.0. The destination it's trying to reach is router 2. Router 2 has this other address assigned, the 192.168.0.2. So when router 1 is generating this packet, and it's trying to send a ping to router 2 or to any other network traffic it's trying to send, the first thing it needs to know is this device on my same local network? And the way that it does this is it takes its local address and it runs the AND against the subnet mask. So if we were to look at this in binary, we have 192.168 and 0 and 1. First thing we would need to do is convert these into to binary. So we're essentially going to go through it the long way. This is what the router is doing instantaneously with its own internal binary calculation. But what it's saying is that I have my decimal value 192. In binary, this is 11000000. So that's the 192. The 168 is 101.01.01000. The 0 address is going to be 0. So 0 in decimal is 8 zeros in binary for 1 byte. And then the last address was a 1. So that's going to be all zeros. 1, 2, 3, 4, 1, 2, 3, 1. So this is router 1's address in binary. It's then going to compare it against its subnet mask, where the subnet mask here is 255, 255, 255, 255, or excuse me, 255.0, where in binaries is basically just all 1s for the first 3 octets. So it runs through the truth table. It says that a 1 and a 1 is 1. A 1 and a 1 is 1. For any case that the numbers are different, the result is a 0. So only where the 1s match up is it going to be equal to a 1. This resulting number here is if we were to convert it back, it's 192.168.0.0. This is now what router 1 knows is its local subnet. So whenever you take your own address and you run the binary AND against your mask, it tells you what subnet you're on. So if the mask was something more complicated, let's say it was the address is 192.168.0.84, and my subnet mask is a /27. where we would have the same match here for the first 3 octets, but the last one in 84 is 1010100. Then the calculator leaves off the leading 0. So this is 84 in binary. Then a subnet mask of a /27 is going to be these first 24 bits plus 3 more. So these would be 111. The result of this would be 192.168.0100000, which means that this value here, if we were to convert it back, so in binary this is 1000000, this is a 64. So that last octet is a 64. This means that this subnet would then be 192.168.0.64/27. So this is the subnet address. So when router 1 is comparing against router 2, is that other address, the .2 in my network. If we were to run the same operation of the 2, so the only thing that would change here for the .2 is this would read 10. The end result is going to be the same. 101.01.0.0.0.0. So this equals 192.168.0.0. Since this result here is the same as what router 1 came up with, it means that this address and this address, they're on the same layer 3 subnet. Now when we look at this in comparison to the OSI model, the layer 3 network layer is where IP is working. Layer 2 is where we had Ethernet. Then layer 1 here, this is our physical network. So these are our copper cables. When this host here now, router 1, 192.168.0.1, is trying to reach the other one, 192.168.0.2, this calculation that it's doing at layer 3 with the binary AND says we're both on the same network, 192.168.0.0/24. What they then assume is that they're also in the same layer 2 network. Or in the case of Ethernet, the layer 2 network is defined by what? Is defined by the VLAN. So router 1 is going to assume that from an Ethernet point of view, we should be in the same VLAN because your IP subnet should map to your layer 2 network. Because the VLAN controls what from the switch's point of view? It's going to control who is in the same broadcast domain, or who can send that layer 2 packet that goes to the all Fs. Now the reason that these two relate to each other, that how we end up in this binary AND result and how IP is going to work with Ethernet, is we have that protocol that is the Address Resolution Protocol, or ARP, where IP is working at layer 3, Ethernet is working at layer 2. So layer 3 is using the IP addresses, layer 2 is using the MAC addresses. So the hosts that want to run IP version 4 over Ethernet, they need to do a correlation between these two. They need to know what is the IP address that corresponds with this particular MAC address. So when the data actually moves down the stack and it goes from layer 2 to layer 3, the layer 2 process is going to say to the layer 3 process, I know where you're trying to send the packet, but I need the layer 2 address because I'm using the MAC address, not the IP address. And this is what Address Resolution Protocol is trying to provide us. That the idea is that when I figure out that I want to send an IP packet, and it's going to go over Ethernet. I now need to know what's the MAC address that corresponds with that. So I'm going to send my request to the all Fs address. The other device is only going to receive this if what is true about the Ethernet network. So if I send a layer 2 Ethernet packet onto my LAN that's going to all Fs, who's going to get it? Everyone in what, though? Everyone just in the broadcast domain, or basically everyone in the VLAN. So if they're in the same VLAN as me, they should get that broadcast request. So ARP is basically asking, with that layer 2 broadcast, who has this particular IP? Trying to figure out for the address WXYZ who is assigned this. If that device is in the same VLAN, or in the same broadcast domain, it's going to hear the ARP request. It says, that's my address. My address is WXYZ. So I'm then going to tell them, this is my MAC address that correlates to it. It's 1, 2, 3, 4, 5, 6, 7, 8, whatever. But the key is that this operation with the IP address and the subnet mask is then going to control who do you send the ARP for. Is the ARP supposed to go for the final destination, or is the ARP supposed to go to some intermediate router that needs to route the packet on my behalf? And this is what the subnet masking is going to allow us to do. So when we run that operation at the binary AND, if their destination ends up to be on the same network as me, it means that the ARP request is going to the final destination. So in this example between router 1 and router 2, router 1 is going to send the ARP saying that the layer 3 source IP address is me. The layer 3 destination address is router 2. The source MAC address is going to be whatever router 1 is assigned. The destination MAC address is going to be the all Fs, because I don't yet know what is 2's address. So if they're in the same VLAN, router 2 should receive this, and then the reply should come back in. Now in this case, we can see from router 1, the ping didn't actually work, which most likely means that they're not in the same VLAN. So assuming there's nothing wrong with our cabling or that the IP address isn't configured wrong, if the devices can't communicate on the same subnet, it means there's something wrong with the layer 2 network. And this is why our basic ICMP ping is a really good network troubleshooting technique. That I know up to this point, there's something wrong below layer 3. So if we were to correlate this with our physical diagram, router 1 is connected to switch 1 on this port. Router 2 is connected to switch 2 on this port. So this means that if I am going to have end-to-end connectivity between them, whatever the VLAN number is that switch 1 is assigning has to be sent over this link, which is going to be my VLAN trunk, and it has to be the same value that's assigned on switch 2's port. Otherwise, we won't have local communication in the LAN. So let's go through the basic troubleshooting of this before we go on to the rest of the routing. So I want to know, why was router 1 not able to reach that destination? If we were to look at the show ARP, most likely what we're going to see is that there's an incomplete entry that goes to router 2's address. So if I send this ping and it doesn't go through, when I show ARP, router 1 says, I asked this destination what their MAC address was, but I never got the response from them. That's what incomplete means. Since this is going to the all Fs, it now means there's something wrong with Ethernet at layer 2. So next, let's look at, is there something wrong with maybe like the physical cabling? How can we check on router 1, is this actually the correct interface that we're connected to on switch 1? Okay, one thing would be to look at the show interface status. So if we show IP interface brief, on router 1, I need to make sure that it shows what here? That the link status is up and that the line protocol is up. So this tells me there's nothing wrong with layer 1 there's nothing wrong with layer 2. So it's probably not related to the interface itself. So next let's look at, am I actually attached to that interface that I think I am in the diagram? We can figure this out by looking at the show CDP neighbors. It says my CDP neighbor is switch 1. My local interface is fast Ethernet 0/0. The link that they're using to get to me is fast Ethernet 0/1. So it's a quick way to correlate, is my diagram actually matching what's going on in the physical cabling in the network? So that looks fine. Okay, let's go to the next device, which is switch 1, and see if the connection over to switch 2 is correct. From switch 1, let's do the same thing. Let's say show CDP neighbors. It says that switch 2 is attached on 2 different interfaces, fast Ethernet 13 and fast Ethernet 14. Now, I don't really care which one of these that I'm using to get there, as long as one of them is used and that the MAC address of router 2 should be installed in my local table. Because if the VLAN is end-to-end, it means we're in the same layer 2 broadcast domain. It means that I should know router 2's MAC address. So let's go to router 2. I want to know what is the MAC address. If we show interface fast Ethernet 0/0, here's the address. On switch 1, if we look at the show interface status, it says the link that's connecting to router 1 is in VLAN 1, so it's in the default VLAN. This means ideally router 2's MAC address should also be in the VLAN 1 table. When we look at the show MAC address table dynamic for VLAN 1, I should be able to see this one. Which ends in C880, which I don't see. Let's look at switch 2 and see if switch 2 sees that. Let's say show MAC address table for the specific address. Says this is learned. I do know about router 2's MAC address. It's reachable on port fast Ethernet 0/2. It's dynamically learned. The VLAN number is 101. This is going to be what the problem is then. That the traffic can't move between the VLANs since they're not in the same broadcast domain. So router 1 is trying to send that packet that's going to the all F's address. 2's not getting it because we can't send broadcasts between separate VLANs. And this is going to be one of the fundamental differences between layer 2 switching and layer 3 routing. That layer 3 routing can move packets between VLANs, but it has to do it at layer 3. Where Ethernet VLANs, these work at layer 2 just by looking directly at the MAC address table. So let's change that assignment on switch 2. If we look at the show run interface fast Ethernet 0/2, the problem is that this is just in the wrong VLAN. So I'll move it back to the default one. Switch port access VLAN is 1. On router 1, if I look at the debug ARP, this should show me the actual communication between the two of them. So when I send the ping, I'm going to ask router 2, what's your address? So I'm sending the packet to the destination IP address of 192.168.0.2. The source IP address is coming from me, and I'm telling them what my MAC address is. So now I got a reply. It says the ARP reply came from 192.168.0.2. It told me this is their address. The destination was coming back to router 1. So essentially this means that the ARP request is a broadcast, but the ARP reply is a unicast. So the request is asking everyone, does anybody have this address? Once the receiver gets it and says, this is my address, I'm going to send the single reply back to them saying, you're the one who was asking me, I'll give you my layer 2 address. So now on router 1, if we look at the show ARP, we see that since these devices are in the same layer 2 network, we did the direct resolution between them. Now, the only reason that router 1 sent this ARP to begin with is that it masked its own address against its own subnet mask. Then it masked the destination against its own subnet mask, and it figured out they're in the same subnet. If we were to look at this same output of debug ARP, and let's say I send traffic to any other random destination, 1.2.3.4. In this case, router 1 is not going to generate an ARP because when it masks this address, they end up to be in different networks. So the key is that this process with the address resolution is that if I figure out the destinations in my subnet, I'm going to send the ARP directly to them. If it turns out that the destination is in someone else's subnet, then I'm going to ask the default gateway to route the traffic on my behalf. Now, in the case of the routers, they're the ones who are actually doing this process. So a lot of times you'll see that they won't have a default gateway. They're going to run some protocol that's exchanging the different networks that are in the topology. But for the first example here, we're going to do it with just static routing. That's going to make it look basically like we have default gateways. And we'll see the key is that once this process happens, it's going to happen over and over and over through every router that we have to move the traffic through the network. That they're going to be changing the information that's in the layer 2 frame every time an IP packet moves between its interfaces. And this is one of the key differences between routers and switches. That for an Ethernet switch, if I were to have host A connecting to host B, and in the middle, A is connected to switch 1, switch 1 is connected to switch 2, switch 2 goes to host B, as long as this broadcast domain is the same one end to end, which basically means they're in the same VLAN. Let's say they're in VLAN 1. When A sends the IP packet this direction, okay, assuming we're running IP, the IP source address is going to be A's IP. The IP destination address is going to be B's IP. The MAC address source is going to be A's MAC address. The MAC destination is going to be B's MAC address. Because we're assuming that if they're in the same layer 2 network, they should be able to talk to each other directly with Ethernet. But if we were to take this same design and put a router in between them, so let's say now we have A going to switch 1, switch 1 goes to router 1, router 1 goes to switch 2, switch 2 goes to B. And this device is routing IP, so we're going to have two different subnets assigned. Let's say on this side we have 192.168.0.0/24, and on this side we have 192.168.1.0. A is address.1, B is address.2. The layer 3 IP packet is going to look the same whether we're sending it over the same LAN or whether we're sending it over the routed network. So when A does the IP source address, it's going to be A's IP. The IP destination address is going to be B's IP. The MAC address source is going to be A's MAC address. but the MAC address destination is going to be router 1's MAC address. Because when this end host runs the binary AND of 192.168.0.1 and my mask /24, then compares this result against 192.168.1.2 and /24, these end up to be different values. So this is how A figures out that I'm not in the same IP network as B is. So I need to send my traffic to an intermediary router, or basically the default gateway. So A would have to know that to get towards this destination, I need to go to this router first. Let's say they're the .254 address. So when the IP packet is sent, we have the IP packet and then whatever's inside. Let's say we're doing a ping. When router 1 receives this layer 2 header, the Ethernet header, it's going to remove this, it's going to decapsulate it, and it's going to build a new one. So it has a new layer 2 header as the packet is then routed out the opposite link. So it has a new layer 2 header, but it has the original IP header, or the original IP packet, and then the original payload inside of there. So when B receives the IP packet, it's going to see that the IP source address is A. The IP destination is B. The MAC address source is now router 1's MAC address. The MAC address destination is B's MAC address. And this procedure that router 1 is doing, sometimes it's called the layer 2 packet rewrite, where on a hop-by-hop basis, as the router is moving traffic between its interfaces, it's removing the layer 2 header as the packet comes in, creating a new one before it sends it out the other link. This is why when we look at switching here inside the same VLAN, sometimes this feature is called transparent bridging, because the switches don't change anything in the data as it's moving between the interfaces. But with IP routing, the packet is changing for every single hop that it moves through the network. So let's look at a basic example of this now, where right now we have the Windows machine that has the address 192.168.0.100/24. And it has this physical connection that's going to switch 1. Switch 1, we're going to set it to be the Windows machine's default gateway. And the way that we're going to do this is to configure a layer 3 interface on the switch that is VLAN 1. Okay, that's the VLAN they're assigned to. And I'm going to give this an address. Let's say 192.168.0.254. The switch is then going to have a different VLAN. We'll say VLAN 2 that's going to router 1. This is going to now be in a different IP network. So we're going to change router 1's address to 192.168.1.0. The switch is going to have both of these interfaces running IP. One of them for VLAN 1, one of them for VLAN 2. So the next step on router 1 is I'm going to change its address to be 192.168.1.1. You'll see that right now I was still issuing that debug ARP command, which is showing us the layer 3 to layer 2 resolution, which is the IP address to MAC address binding. Router 1 figured out that there was a problem, that I was getting replies for people that are not in my subnet. It's trying to tell you that there's something wrong at layer 2. I'm on the wrong cable, or I'm on the wrong VLAN. But we can ignore this for now because we're changing its assignment. Now additionally, the routers have this command on by default that is IP routing. For now, I'm going to turn this off, no IP routing. This is going to make it look like it's an end host. And what this is going to allow me to do is issue the IP default gateway command. And I'm going to set the default gateway to 192.168.1.254. So it's now basically the same as like your end host, that your end host has an IP address. Then for anything in this subnet, I'm going to send it directly to those destinations. But anything in a different subnet, I have to ask the gateway how to get there. This gateway address, this is going to be on switch 1. So on switch 1, I'm going to have two different layer 3 IP interfaces. One for VLAN 1, that is 192.168.0.254, and one for VLAN 2. The switches, on the other hand, have IP routing off by default. So on that, I'm going to turn routing on. And the reason that I can do this is this particular platform this 3550, this runs an iOS software, a Catalyst iOS software that allows you to do layer 3 routing. So it's a layer 2 Ethernet switch, but it's also a layer 3 IP router at the same time. If I now look at the show IP interface brief, the switch has two separate VLAN interfaces. Sometimes these are also called SVIs, or switched virtual interfaces. It basically means you're acting like a router, but there's no physical port that this is assigned to. So any port that is assigned to VLAN 2, they should be able to reach this IP address. Likewise, any port that's in VLAN 1, they should be able to reach this address. So now from a VLAN assignment point of view, I'm going to have router 1 in VLAN 2. And the Windows machine, this is going to stay in VLAN 1. So on the switch, I'm going to go to router 1's interface and say switch port access VLAN 2. It says the access VLAN does not exist. I'm going to create it for you. Basically what this means is that I skipped a step where you would normally say this for VLAN 2 to create the VLAN. But the switch allows you to skip over that. If you assign it and it's not created, it'll just automatically create it for you. Then the port that goes to the Windows machine, this is going to be switch port access VLAN 1. Then on router 1, we're going to look at two things: the show IP ARP and the debug ARP. So I want to now know what are the IP address to MAC address associations that router 1 is going to have. On the Windows machine, this is going to be the equivalent of looking at the ARP-A, or essentially show me all entries in the ARP cache or the ARP table. Additionally, if we look at the ipconfig/all, this machine has the address 192.168.0.100. Its subnet mask is /24. The default gateway is 192.168.0.254. So in other words, it's switch 1 is the gateway. When I now send an IP packet that is going to 192.168.1.1, the Windows machine internally is going to say that this host is not in my layer 2 network. Because the TCP/IP stack, or basically the IP software on Windows, is going to say, look at my address, which was this value here. Look at 192.168.0.100. Run the binary AND against the subnet mask. The result of this is 192.168.0.0. Then take my subnet mask and run an AND against this. The result is 192.168.1.0. Since these two results are not the same, the IP stack knows that I now need to ask the default gateway how to get there, because we're not in the same IP subnet. So eventually we can see that the pings work. So I'm able to now route the traffic between the two different networks. But if we look at now the ARP-A, so asking what the ARP cache is, the entry that the Windows machine has is for the gateway, not for router 1. So it's saying that since this destination is not in my subnet, I know that I need to route to get there. And I don't have routing protocols configured. I just have a default gateway, or basically a default route, pointing me to the .254 address. So when I build an IP packet that's going to router 1, the Windows machine is going to say that the source IP address is 192.168.0.100. The destination IP is 192.168.1.1, so it's going to router 1. The source MAC address is the Windows MAC address. The destination MAC address is switch 1's VLAN 1 MAC address, or the switch virtual interface VLAN 1. When router 1 receives this on the other side, if we look at the output of the ARP, debug IP ARP, or debug ARP, it says an ARP request was received. The source IP address was 192.168.1.254, which this here is switch 1's VLAN 2 interface. Switch 1 is saying that for my VLAN 2 interface, this is my MAC address. I'm asking this IP address, which is router 1, what's your MAC address? So since this is my address, I'm going to send them the reply. I'm telling switch 1 that this is my MAC. If we now look at the show ARP, we see that the only other entry that router 1 has is its gateway. So the key here is that when the traffic needs to be routed between the subnets, you're going to use the layer 2 address of the gateway. But if the traffic is going between the same subnet, then it's going to go for whatever the final destination is. So if we were to look at the Windows machine again, and let's say for traffic that's staying inside of VLAN 1, which includes router 2's address. If we were to go to router 2 and look at the debug ARP, then if the Windows machine were to ping 192.168.0.2, which is router 2's address, 2 is going to be receiving that directly from them. Because when the Windows machine masked its own address against routers 2's, they ended up to be on the same network. They're both on 192.168.0.0. So this also means that the layer 2 switch, which is switch 1, if we were to show MAC address table for VLAN 1, in this table it's going to have the MAC address of the Windows machine and then also the MAC address of router 2, which if we look at this ARP reply, it should be this value here, 000C29F8 A35E, which is this, no, that's the Windows machine. I am C880. This is router 2's. C880. But router 1's address, this BC20, that MAC address is not going to be in the VLAN 1 table. That MAC address would be where? It's going to be in the VLAN 2 table. So the switch is still going to know all of the Ethernet addresses for anyone who's in its same LAN. The key is that when it's routing the packets between the interfaces, it's routing it between the VLAN 1 and the VLAN 2. I'm receiving packets in from the Windows machine. I'm taking off the Ethernet header. I'm taking off the MAC address. And I'm replacing it with a new packet that comes from my own MAC address, which again is the layer 2 packet rewrite. So we'll see that as we start to get into larger designs where there's multiple routers connected together and they're working over different types of layer 2 protocols like Ethernet versus frame relay or PPP, HDLC, that the key is that the router, when it moves its IP packets between interfaces, it's always performing this, the layer 2 packet rewrite. It has to rebuild the layer 2 frame. So it needs to know who is the next hop device on that broadcast domain, or basically that VLAN, in order to get to the next destination. So let's add some other devices to this topology now. Let's say that router 5 is going to be now part of router 1's VLAN. So we'll have router 5 in VLAN 2. We're going to give it a new address here, 192.168.1.5. And I'm pointing its gateway to switch 1's VLAN 2 interface, which is 192.168.0.254. So now on switch 3, I'm going to change this VLAN assignment on the port. On Fast Ethernet 05, we'll say switch port access VLAN is 2. Now I need to make sure that all of the switches in the middle, that they all have VLAN 2 created. So on switch 2, I also need to say this VLAN 2. Now on router 5, this is Fast Ethernet 0/1. I'm going to change its address so it's in 192.168.1.5/24. Then I'm going to ping router 1's address. And we'll see it's going to take some time for layer 2 spanning tree to converge before I can send the packets. So after about 30 seconds, I should be able to reach router 1. So now 5 and 1 can reach each other. If we look at the debug output on router 1, it says that the ARP request was received directly from router 5. Came from 192.168.1.5. Because when router 5 compared this address against its own subnet mask, it says we're in the same network. So I'm going to send the ARP directly to them. If I'm in the same IP network, I'm going to assume that I'm in the same VLAN as well. So the packet goes out to the all F's address. Router 1 gets it. It says this is my address they're asking for. So I'm going to send them the reply. telling them that this is my MAC address. But if I were to send traffic to the Windows machine, and on router 5 I'm also going to debug ARP. That's ping 192.168.0.100. And actually I skipped one step. What I would need to say here first is no IP routing and set my default gateway. So router 5 for right now is disabling the routing process. It's treating itself as if it's just an end host. And it has the gateway set. So now when I ping to router 1, there should be a direct ARP request to them. So we can see it says the IP destination is 192.168.1.1. It's coming from my address 192.168.1.5. But if I were to send traffic to the Windows machine who's in a different network, the ARP reply is going to come back from, and let's see, you know what, this is on, I have multiple addresses here now. I want just that single address. And let me refresh this. Okay, so 5 again sends traffic to 1. They're in the same network. It's going to ask 1 for its address, for its MAC address. Once layer 2 spanning tree converges, we should get the response directly from 1. We received the reply from router 1. Router 1 told us this is its MAC address. If we look at the show ARP, we see we directly know 1's address. But if we now send traffic to the Windows address, the ARP reply is coming from who? It says received a reply from switch 1's VLAN interface. And this is the key difference, that if they're in the same subnet, they ARP directly for each other. But if they're in different subnets, they have to ask the gateway. So now I only have to maintain the MAC addresses, basically for the devices in my local LAN. If we now look at the show ARP, 5 doesn't need to know the MAC address of the Windows machine. It only needs to know the devices that are in its same VLAN, inside of VLAN 2. So technically, these MAC addresses, they only need to be unique inside of the individual VLAN. I could have router 5's address, router 5's MAC address, configured as 000000000005, and then do the same thing in Windows. There's not really any reason why you would do this, but you can. Because when 5 talks to the Windows machine, they're not talking directly at Ethernet at layer 2. They have to route the traffic to each other, which means that switch 1 is changing the MAC addresses as it's moving between the interfaces.
So in your example, the only place that the layer 2 packet rewrite occurred was when you sent pings from the Windows machine?
Between the two separate VLANs. So if the traffic is moving from
Trying to figure out where the rewrite at.
okay, if the traffic goes from 5 to 1, switch 1 does not change the packet at all. But if it goes from 5 to the Windows machine, it does change the packet. Because this is a routed packet. This one that goes to router 1, this is bridged. So the transparent bridging process, or like the layer 2 switching, it doesn't change anything in the frames. Only the layer 3 routing process does. So if we were to put a packet analyzer on the link, like on the link here and then on the link here, you would see that the MAC address is changing as it's moving between the different interfaces. So this is the main key point about IP routing, that every time you move the packet between a routed interface, you have to rebuild the layer 2 header. The layer 3 header still stays the same, the IP packet, where you have your original source and your original destination. But if we were to think about this from the terms of like internet routing, let's look at let's look back at that route server we were looking at before. And the IP address that we're using here. So this is the public address we have. From this internet router, if they were to send traffic back to us, and probably someone is filtering out the pings because of security reasons, but what I could do is do a trace route back to this address. For every hop that this shows, so there's 9, 10 hops between us and whatever this router is, each of these devices is changing the layer 2 frame, because it has to be routed between this address 12.0.1.202. It has to be routed to the next router in line, which is 12.89.5.13. And it's changing over and over and over until it finally gets to whatever our gateway is. Then when we receive the packet, the MAC address would be coming from the gateway. But the IP packet still is coming from this device that's originating the layer 3 frame. Okay, any other questions up to this point on the basics of the IP routing process? And again, this is one of the reasons why that we don't really care what the MAC addresses are in the network, because the IP stack is automatically going to talk from layer 3 to layer 2 to figure out how to resolve this with the address resolution protocol. The only case that we would care about is that if for some reason ARP is disabled, and most of the time you wouldn't do that. So it's an automatic protocol that runs between Ethernet and IP to figure out what's the next MAC address that's in line along the path. Then as long as we can just keep track of what are the IP addresses we're trying to reach, then that's all that we really care about.